Great. Well, we're really excited to welcome Tom Zahavy, who is a senior research scientist at Google DeepMind in the discovery team led by Satinder Singh. Before that, he was a PhD student at the Technion. Tom is interested in building artificial intelligence systems that make decisions and learn from them. His focus is on the reinforcement learning paradigm, where he studied aspects of interpretability, scalability, structure discovery, hierarchy, abstraction, and exploration. He was one of the first researchers to work on RL for Minecraft and language games. More recently, his research focused on learning to RL learn, metagradient RL, unsupervised RL, convex MDPs, diversity, and bounded rationality. And if you want to know more about his work, you can find it on his webpage, which is linked at the top. We're really excited to have Tom, and you can take it away from here.
So thank you again, Eugene, for the invitation and for the introduction. I'm really excited to present this work. We've been working on this for quite a while. And since we are not a huge group, feel free to stop me and ask questions. I think we'll be fine with time. Cool. So this work was done with this great team of collaborators at DeepMind, over a year of work. But the ideas and that led to this work, I've been working on them for quite a while. So I've been interested in diversity for quite a while, and it took us time to say, okay, let's try it in chess. And once we kind of started to get excited about this, it was really getting interesting. So to give you some context, we took a very hard challenge, like trying to address creativity, and creativity has many definitions in different paradigms and domains. So we tried to focus here on a specific definition of creative problem solving, and this definition is coined by Osborne. It's not very surprising, so it's the ability to generate creative and innovative ways to address a problem. And essentially here we mean that if we can solve the problem in one way, then solving it in a creative way means that we find alternative ways to solve the same problem. Now, these new ways can be new to humanity. So there's been a lot of papers analyzing how AlphaZero changed the game of chess by introducing new ideas. So some famous examples are the pushes of the H and the A pawn, and a lot of sacrifices of material. There's some papers that analyze and show that they changed the game style of Magnus Carlsen. But here we'll focus more on new ideas that are ideas to the agent, or ideas that are new to other agents. So really how to discover ideas that the agent wouldn't have thought about them before. And diversity will play an important role here. Yeah, so for some motivation, I've read this great book called The Diversity Bonus by Scott Page. And this book is a book in the social sciences, and it basically analyzes how teams that have different kind of thinkers can outperform homogeneous teams in complex tasks. And what's important here is that the task really has to be complex. So we don't want a task that a single individual can solve if it's really good. We really want tasks that a single individual can't solve most of the time. So like in our example, it's going to be like very hard puzzles that, one agent wouldn't be able to solve all of them. But in other tasks, it can be just something that is very challenging. And this work is basically trying to bring these ideas and to see if they can be applied to superhuman AI. So, when we build very strong AI systems, it's not clear that they have to be different or that they can be different. And we wanted to test this hypothesis to see if we really can build very strong AI systems that can also be different from each other and complement each other in a very challenging domain. So there's this hypothesis on computational rationality. And essentially, we mean that games like Go and chess, they are too large and we can't solve them optimally. And the performance at the end, it depends on compute. So for those of you who don't know, we cannot fit a neural network to play chess very well. So the best neural network will play at around 2000 ELO if you just let a flat neural network play. And all the neural networks will improve if you allow them to do some planning and get better with compute. And this is a huge gap. So neural networks typically go from 2000 ELO to around 3600 ELO if you allow them to do some planning. And on the puzzle evaluations that I'll show later, we will really see monotonic improvement with the number of computations that we allow the neural network to do. So the point here is that we can't compute the optimal policy in chess because the game is just too large. So we limit ourselves to these computable policies. And within the computable policies, potentially there are multiple suboptimal policies. So we can find, with whatever computational budget we have, we can find those different suboptimal policies in the dots here, and they can be different in principle. So the question is how much room there is there for diversity is an empirical question, but this is our argument, that basically if we'll find multiple policies like that are suboptimal, then we will enjoy increased creativity. And the goal here is to test this hypothesis with AlphaZero in the game of chess. There's been a very nice article at chess.com on positions that computer cannot solve. And usually those positions are closed positions, like the one here, that require some manipulation of the pieces. But some of them are simpler, it's been kind of a race between human players and AI systems. The humans are always interested to identify those positions that human cannot solve, and there's lots of threads on them and blogs, because usually humans can understand those positions with enough time. So it really shows that there's still some gap in understanding, or still some gap in how we as humans approach chess, and computers still have this limitation. So those puzzles are not adversarially created, related to your original question, Eugene. They are just puzzles that human created, and for some reason machines can solve them, and I'll try to shed some light on why is that. Yeah. So a little bit on quality diversity in chess. So in general, chess is a game where computers are mainly measured by strengths. So at the end, we only care about scores like ELO and win rate. But there are some notions of diversity in the game of chess. So this is a quote from Demis, where the bishop and the knight were traditionally scored equally by traditional chess engines. So the chess scoring system is usually like 1 for a pawn, 3 for a knight or a bishop, and 5 for a rook, and 9 for a queen. And then bishop and the knight were originally scored equally, but they behave very differently. So there is some tension there in diversity between how these moves play and the score that they are given. Another notion of diversity, so this is from the Understanding AlphaZero paper by Nenad Tomasev and Tom McGrath. So here they showed the different checkpoints of AlphaZero, ended up preferring different opening variations in the Ruy Lopez. So essentially, opening theory in chess, it evolves like a tree, and in many of these openings, you can play different moves, and all of these moves are considered playable or equally strong. So humans cannot say this move is better than the other. And this is an empirical observation that different checkpoints of AlphaZero actually ended up preferring those different variations. So you can have diversity in the opening theory in principle in chess. So it's not like a computer has to choose a single line and that's it. Another evidence, so if you follow Magnus, the way professional players prepare to chess games today is that they do a lot of preparation with computers on a position, and they try to look for moves that the computer missed. So sometimes the computer will miss the move at shallower depth and not at the deeper depths. And here the move that I'm showing on the right is a famous example from one of the chess world championships, where one grandmaster did a preparation for the game and actually missed the winning move. And the other grandmaster actually played this winning move and won the game. So the interesting thing here that people actually look for the less playable lines. So they look for moves that are less preferred by computers, and then they try to see if they can play them. Because if you do that, you can kind of surprise your opponent. So it just shows that humans use chess engines in different ways, and the diversity is actually a really important part in how they're being used in practice. Okay, so going to this work, what we propose here is essentially to build a league of qualitatively diversity AlphaZero agents. So we want to find all of these suboptimal policies that I showed at the previous slide. And the way that we are going to do that, so if we start with AlphaZero, AlphaZero is a neural network that gets the chessboard as an input and outputs a prior and a value, and then performs MCTS search on top of this prior and value. So what we are essentially proposing is to model a league of agents with a single latent conditioned architecture. So what it means is that for each player I, we are going to have some latent variable Ti that will be added as an input to the network, and that's how the network is going to model this player. It's a common technique. People use it for diversity in many other works. Now, once we have this latent variable, we're also going to give an intrinsic reward that will motivate the policies to play different from each other. And I'll explain about this intrinsic reward in depth in the next few slides. And this intrinsic reward is essentially being added to the value of AlphaZero while it's doing planning. So we are going to plan with this intrinsic reward in order to maximize diversity. The last part is that we are also considering a matchmaker. So we are going to match different players in the league against each other. And this matching mechanism can be just in uniform. So we can just match player I against player J. But we can also consider more complicated techniques like PSRO or rectified PSRO or anything else that you've heard about for how to match the populations against each other. Yeah.
Do you have to change anything on the neural network architecture side to make it like work well in this latent condition setting, or is it just the standard network used in like AlphaZero type work, and it just works to add this like intrinsic diversity and latent conditioning, just like works out of the box?
So it takes some time to find the right representation. Here it wasn't too complicated. So the representation in AlphaZero is essentially some representation of the board, and then you have some bias planes for scalars, and these scalars can be some counters of the game, the ability to castle. So there's already support for discrete variables in the representation. And here we are basically just adding another bias plane to represent the latent. So in terms of size, it's not adding a lot. It's not increasing the input by a lot, and it was sufficient for modeling what we needed. We did explore quite a lot in this space, so we tried stuff like film embeddings and stuff. But we couldn't identify that one was significantly better than the other.
Great, thanks. Yeah, I just found it really interesting that like the initial architecture had enough capacity in it to represent like different styles of play. Yeah, thanks.
Cool. Yeah, another question? Pranay, you have your hand up?
Oh, my mic was off. I'm sorry about that.
No,
It's never happened to me before on any voice platform. Did you just have to add one neuron to represent this particular thing? For some reason, I heard that. And
so it's not one, it's another bias plane. So it's essentially more input planes, and then the number of convolution, they just get more input channels, and we maintain the same output channels in the last layer. So no big changes to the architecture, just changes to the input. Cool.
All right, thank you.
Welcome. Okay, cool. So with this, I'll move to methods. And I wanted to start with like a high-level overview of this regime of quality diversity. So there are different approaches for quality diversity, and there's a nice website summarizing all of the work done on this topic. This theme started with this paper called Map Elites by Jeff Clune. And essentially what they do here is that they collect a list of networks. So they maintain kind of a collection of networks, and then they do some mutations to these networks, and they only keep the good ones. So this is kind of parameter diversity, because they want to have this basically different agents that have different parameters from each other, and they all perform well. And this approach is working really well in smaller domains. Usually beats methods like Diane that you guys may be familiar with. but it's hard to scale them to larger domains, and this is a very active field of research at the moment. The kind of diversity that I'll focus on is more similar to Dayan. So I'm going to focus on methods that make the agent to behave in different ways. And these are just some examples, and I'll expand more on that. And the last kind of diversity is response diversity. So this kind of diversity is more common in multi-agent communities. And it's mainly used for these non-transitive games, for intransitive games like rock, paper, scissors, where you can get cycles in the response space, and by adding diversity, you can make the agents to conquer niches in the agent space. And another point to comment here on the high level is that some of these methods use these collections of networks or collections of architectures, like in QD or in population-based training that you might be familiar with. And some other works model the population using this latent conditioning. Latent conditioning is usually more efficient in terms of memory and training time, but sometimes it's tricky to get right. So this is like a short high-level overview, probably not extensive, but it will be enough for this presentation. Yes, Kevin.
Yeah, I got a quick question. Can you explain why the map elites will optimize for parameter diversity and not behavior diversity?
So the lines are today blurry between all of these methods because some take ideas from other places. This is more to say that if you collect a set of parameters, a set of agents by simply having them different parameters, that's kind of implicitly what you optimize for. And if as a result you also get behavioral diversity from that, then that's great. It's more like just an observation for how these methods work. They work by collecting these different networks. Is that answering your question? Yeah.
Yeah, thanks.
Okay. So I'll need to define what a state occupancy is. I hope that you guys are familiar with this, but if not, it will be short. So in RL, we usually follow a policy in some MDP, and a state occupancy is essentially a distribution over the states and actions that you see if you follow this policy for a long time. So here I'm writing it in the tabular formulation and the discounted form, but this concept of state occupancies can be applied in any form of MDP. It can be in a finite horizon MDP, it can be in an average reward MDP, sometimes it's associated with mixing and mixing times and stationary distributions. But essentially, the way you need to think about the state occupancy, it's a distribution over states that you will see if you will follow a policy for a long time. And if you have a state occupancy, then your value function becomes just a linear product between the state occupancy and the reward. Because now you have a distribution over states and action, and the value function is just the expectation under the state occupancy of the reward. So the reward is basically weighting states and actions, and the value is the expectations, the expectation of that. And people defined all sorts of general value functions that can also be written like that. So for example, successor features can be just expectation of some features over the state occupancy. So the state occupancy, again, is just a distribution over states. Okay. Now, as I mentioned, in the standard RL problem, we just want to maximize this inner product between the state occupancy and the reward. But we can write it in the dual form, and in the dual form, you will see that it's just a linear product between the reward and the state occupancy, and these two problems are completely equivalent. So, we can think about them in different ways, but mathematically or in terms of optimization, these are two equivalent problems. And this is relevant because now I'm going to write another optimization problem where we try to minimize some function of the state occupancy. Okay, so before it was a linear function, and now we just look at some arbitrary function of the state occupancy. And you can say, okay, what this function is useful for. So there are different examples. So for example, in apprenticeship learning or imitation learning, sometimes the formulation is just to minimize the distance between the state occupancy of the agent and the state occupancy of some expert. So there's a way to define apprenticeship learning like that. And for exploration, people sometimes use this maximum entropy exploration, where you just maximize the entropy of the state occupancy. And for empowerment, people familiar with Dayan or with Gale, you can just define a distance between state occupancies in KL distance and get diversity from that. So what I'm going to is that we are going to define diversity in terms of distances between state occupancies. And what we need for that is some notion for how to optimize this, right? Because if we look back at RL, in RL, okay, we have reward, we tell the agent to maximize the reward, and that solves the problem. We want to get something similar like that for general functions. Okay, so this part of the work is related to earlier papers that we did on this topic. And essentially, there's a very simple trick that if you start with a problem like that, you apply to it a tool that is called differential duality, and you can transform it to a minimax problem, which people in multi-agent RL probably are familiar with. But here the game is between the state occupancy of the agent and this lambda, which is just the negative reward or the cost. So essentially, you play a game against the reward, and you just locally, the problem is linear in the reward here, so you can treat it like an RL problem. And that's the entire point here, that essentially, if you want to solve these general utility problems, you can play this game and maximize this cost lambda, and then optimize the cost separately. Now, at this point, some of you might be confused, but there's a really simple formula for what this cost is. And this cost is essentially just the gradient of the objective. So this is something that we call in the paper the intrinsic reward equation. And basically what it tells you is that if you want to optimize some function defined over state occupancies, in our case, it's going to be behavioral diversity, then you can just take the gradient of this function, treat it as an intrinsic reward, and maximize it using any standard RL algorithm like PPO or AlphaZero in this case. And for this stuff, we have proofs. If the function f is convex, then the sample complexity and everything is almost as hard as standard reinforcement learning. So you don't get extra complexity from dealing with this general utility formulation. Okay. So back to diversity. To define diversity, we basically want to define some distance function between occupancies. And this distance function can be the distance between successor features. This was proposed in the original apprenticeship learning paper, where they try to minimize it, but we can just maximize it instead. And just to show you, in the paper, we showed that diversity is all you need, for example, or empowerment can be formalized as the KL distance between these occupancies. So essentially, most of the methods for optimizing diversity with intrinsic reward, they can be shown that the reward itself is actually the gradient of some objective function, and the objective function is some metric between occupancies. And now, once you understand this connection, you get some degrees of freedom because you can design your reward in the function space. You can design your diversity objective in the function space and then differentiate it to get an intrinsic reward. So this is what we did here. And the idea was to use these successor features to define rewards. And essentially, if you look at this space of policies, if you go back to our example where we wanted to find this diverse set of suboptimal policies, so we can picture all of them on this vector space, and then the reward is just another vector in this space. So we want policies, we want to find policies that will give us high volume in this space and will all have a high correlation with the reward, because that will mean that they are of high quality. So we have this objective that tries to push the distances between the successor features. And notice that here we take the minimum. So for every policy, we want to increase the distance from the policy that is closest to it. and this is called the Hausdorff distance. Now remember this quantity. Yes, Rupali?
Hi, sorry. I'm a little bit confused with the notation. In the previous slide, we had like two d pi's, yeah, here at the top. When we're
Yeah.
trying to find the distance between two policies, so we have d1 and d2, like d pi 1 and d pi 2.
Yeah.
So that means it's the same policy?
Yeah, so
Because
I
the pi is
skipped a few details here. So dpi1 and dpi2 are two different policies, and the 1 and 2 just index the policy. And then here I'm saying, okay, if we want to think about the distance between them, this can be a definition. But then there's a question of how we measure the distance of a single policy from a set of policies, which is what we try to address here at the second equation. And here we take the minimum. We can also take the average, but if we take the minimum, it's this distance that is called the Hausdorff distance. Then we basically say we want to push the distance of our current policy from the policy that is currently closest to it in the set. Does that clear now?
Yeah, and then when we go to the next slide,
Yeah.
I believe the notation changes slightly.
So the indices are still this 1 and 2 policies. So like now we optimize psi I or policy I, and we take the one that is closest to it. So J is optimized over all the indices, not I, from the set. Is that clear? And these psi's are essentially just the expectation of the features under the occupancy. So it's the inner product between those state occupancies and the features. And I'll show an example for how those look in chess in a few slides. You can think of them as just the occupancies of the board. So like essentially how the boards are occupied by pieces on average. But I'll get to that.
All right, thank you.
Cool. Okay, so the point is that now we have a way to get the reward, and the reward is just this inner product between the features and the difference between the state occupancies. This is just direct differentiation. Now, where it gets interesting is that we have more flexibility to define new objectives, and here we took inspiration from physics. So in physics, in solid particles order themselves in according to van der Waals forces, and that's what creates these nice distances between the atoms in a molecule. And what's special about those van der Waals forces is that they combine two forces, one that is attracting and one that is repulsing. So usually you can think about diversity as something that is trying to push policies from each other because we want to make them different. But here the idea is that we can balance it with another attractive force that will actually pull them together. So we basically just built some polynomial in this distance Li, and the distance is just this, just this term here. And the powers of the polynomial doesn't really matter. What matters is that when you minimize this polynomial, it has a minimizer at some point, and we call this point the van der Waals contact distance. And this point is what characterizes the atoms in the solid. So essentially, there's a solution to this that minimizes this objective, and this is the distance that we will get between the policies. So now, instead of optimizing the coefficient of this intrinsic reward term, we have this hyperparameter L0 here that basically specifies what distance we want the policies to be apart from each other. And once we have this equation, we again differentiate it to get some reward, and we use this reward in our agent. Any questions on that? Is it clear at this point? Yeah, cool. Yeah.
I have one. So I think, and I might be wrong, but the Hausdorff distance, does the subset have to be compact? And then, like, can you extend this to the Kuratowski convergence so that, like, it's applicable to essentially, like, unbounded continuous sets. Is that
Yeah.
something you're familiar with at all?
I'm not familiar with this, sorry.
Okay.
One thing that I can note is that because we identified that diversity is trying to push things apart from each other, essentially it's not convex, it's concave. So it's hard to say that it's concave formally, but it's definitely not convex. So you probably cannot talk about convergence here.
Okay.
So, yeah, so the convergence results that we had were for the convex case, and we know that diversity is not convex. Essentially, you can find many different solutions that are different from each other. There's always degrees of freedom, yeah.
Okay, thanks.
Cool. So this is just one example for something that we did in the control suite for finding those quality diverse policies with the van der Waals force from a different paper. Okay. The other kind of diversity that we were trying in this work is this response diversity. And there's strong evidence that it can help in transitive games. So in the Alpha League and later on in works like Nupel. And the idea is that in transitive games, you have these cycles in the response space where one pair can beat the other. And you really, and there are great works showing how response diversity can help in this case. On the other hand, empirically, people observe that there are cycles in non-transitive games like Go, and the later one is an empirical work analyzing human data in light chess. So despite the fact that chess is non-transitive, we thought that it's good to test these ideas also in chess. Disclaimer, they didn't help in our case. So we couldn't find evidence that response diversity helps in our case, but we still thought that it's a good idea to try. Yeah. So just to give a quick reminder for those that don't know, essentially we can control the matchmaking mechanism with different algorithms. So if we do self-play, each player just plays against itself. We can do uniform matchmaking. We can do PSRO, so we can let each one in the population play against the Nash equilibrium. And we had to do some specific adjustments to make it work in chess. So chess is, you don't necessarily have to play the same as white or as black. So we maintain different graphs for white and black. And we studied questions, for example, on how do you control, if you allow them to play against themselves in addition to that, and do you allow them privileged information about the other players? So do you allow them to know what the player is actually doing? And in all of these variations, we couldn't really find strong evidence that response diversity is helping. And that at the end, we used PSRO as a default in this work. Yeah. The last part on methods is on sub-additive planning. So essentially, once we finish training this agent and we get some set of policies that are hopefully strong and diverse, we can try to combine them in different ways. And that's a part that we explored in depth in this work. So we tried many different things, and what ended up working well for us is this sub-additive planning, which is super simple to explain. So let's say that you take some chess puzzle and you have different players in your league. Now you can ask them what is the correct move, and some of them will be correct, and some of them will be not correct. And then you want to select one of them. So essentially, you can use all of the outputs that they have. So you can use the policy or the prior. But what we found out is that if we use just the flat outputs of the network, we could never select the correct player in the position. So we couldn't find anything statistically significant that was right. And what ended up working for us was doing MCTS with each one of these players and getting the statistics from MCTS and then making a decision based on those MCTS statistics. And these decisions are basically just the value. So you can take the MCTS value, and if one agent solved the puzzle, it's likely to have a higher value. So that worked pretty well. But what worked better was a lower confidence bound. So we essentially take the value and we subtract the UCB term. And this technique is kind of the standard in offline reinforcement learning, and it also worked pretty well for us. Yeah. Cool. So let's go for some results. So we started with looking at the policies and analyzing the opening diversity. So what you can see here is some position. We looked at openings, famous openings from an opening book. And here you can see different moves in green arrows that were proposed by different agents in our league. We also show in those numbers statistics from the Grandmaster database. So those numbers basically correspond to how much this move is actually played by Grandmasters and how much relatively win percent they get if they play with this move. And don't mind the specific numbers. The point here is that these moves that were proposed by the players in our league all make sense. So professional players play them. There's nothing surprising about them. So it's very hard to find new ideas in opening theory in chess. But the point is that they do prefer different things on those openings. And if we zoom out, it happens in different positions, not in all of them. Some openings are, you see, like mostly played the same move also by professional players. And on average, we found 2.5 different moves per position in a league of 10 agents. Okay, going back to this feature, successful feature, state occupancy. So remember that we had this distribution of a state that we get by following a policy. And the features in our case are going to be just the piece locations. So the location of each piece in the board and castling rights. Expected features are therefore how much the agent visits a feature on average. So for example, how much the queen occupies a specific square on the board. So in those figures that I'm going to show, each square represents a chessboard, and the colors correspond the occupancy of different pieces. So now it's going to be the white king. Blue is higher and orange is lower, and different rows correspond to different players. Okay, so those are essentially 4 different successor features of different players in the league for the king occupancy. And you can see that the king is in different places in those games, and they basically suggest that there's castling to the king side that happens earlier or later in this case across different players. If we look at more players, we can see that some of them actually castle queen side, which is not very common in chess, but can happen sometimes. And then we can zoom out and start looking at other pieces. So different new columns or new pieces. And here you can see like very weird rook development by one of the players. We can see one player that is playing a fianchetto. So that's when you push one of the g-pawn 1 square up and then take the bishop out from the other side. So we found all of these concepts that are being played by professional chess players and were also being discovered by our players and played differently across different agents. Yes?
Quick questions. Are all these players of similar elo? And is this plot that's being made here, are these agents playing against each other? Like, is that how these rollouts are happening here?
So here the agents are playing with the piece or matchmaker, and this is the empirical distribution of the pieces. Okay. What was in terms of elo, they are all similar. There are some differences, and I'll show one figure on that at the end.
Okay.
But
thank you so much.
Roughly the same elo. Cool. Okay. The next thing that we tested is performance on puzzles. And those puzzles, we became very interested in them. So I'll try to make you interested in them a little bit. So they are very interesting to amateur and professional players. They are used in blogs, books, people watch videos on them. And they're also one of the more common techniques to improve in chess that people will recommend you. They are challenging. So we know that very good chess agents cannot solve all of them. And it's very interesting because the chess community is kind of responding to superhuman AI by trying to find these puzzles, and people get very interested in that. They are valid, so there are legal positions that are reachable. Some of them will look very weird to you, and people found those lines that can actually reach those positions. It's still interesting because in some sense, humans don't try to reach those positions when they create them. So this reachability is actually probably what makes them hard for agents to deal with. We have a few data sets that are large and diverse, and a few that are more small and challenging. And they allow us to measure things quantitatively. We can also hold out some of them and measure performance. And the last thing is probably that they are unique. So some of them allow us to test a chess agent in terms of a strict number, because ELO can move a lot between different things. And here we have this holdout set of positions, and we can just measure accuracy. Just to give you a quick overview, we had 4 data sets. So Light Chess, it's an open chess community, and there's millions of games online. There's a nice data set of puzzles. We filtered it to get the ones that are harder. So we filter them by ELO, and then we pick the hardest ones from them. We got to around 560. Those puzzles are verified by Stockfish, so we know that they are unique. They are multi-step puzzles, so some of them require multiple steps, not only a single one, in order to get a score of 1. And they have different tags, so they can be related to mating X or under promotion, so a lot of different concepts. Just to show you one example, so here you can sacrifice your queen by trying to give a mate, and black can defend by capturing the queen, and then you can deliver mate with the white bishop to the same square, because the king is basically cannot escape because the black bishop is here. So this is a simple puzzle, but there are ones that are more challenging. The other one is the strategic test suite. That's another open source data set, around 1,000 positions that we use. This one has multiple choices per position, and there's a scoring mechanism for how to score the different choices. There's a data set that we collected. It's small, only 15 puzzles. We collected it mainly from this blog on positions that engines cannot solve. But we also found 2 papers written by chess players with some positions that we took. To give you one example, so in this case here on the bottom, you can give a check with this bishop and sacrifice it, and then basically push all your pawns up, because the king can only go to these squares, and then you can close this position, and this is called a fortress. So the point is that once you close this position, it's basically a tie, because either side cannot make progress. So despite the fact that black is winning by a lot of material, if you lock the position, you secure a tie. And computers essentially can't understand that the tie is a tie, because there's also material disadvantage, and they miss this move of closing the position. And unless you make this move, white is essentially lost in this case. The last one was inspired by this article on the Penrose position. So Roger Penrose, he's interested a lot in computability, and he identified those positions that computers cannot solve and wrote a lot about them. Here we try to evaluate the value of the position and give a score if the value estimation of the agent is winning or losing. Okay, I do see that we are running a little bit on time, so I'll try to be a bit quicker. So here is the leaderboard. Here we compare AlphaZero with one of the players in our league. Another score that is the max over the players. So here we give 1 if any of the players was able to solve the position, and it kind of show you that as a group they can solve more. And the last one is with sub-additive planning. So it's when we do this sub-additive planning and select one of them. So what you can see is that AlphaZero, just latent-0, one of the players in the league, they're roughly the same. So sometimes one of them is slightly better. But if you look at these group numbers of the max over the players and the sub-additivity, they are much better than AlphaZero. So you can get a lot of improvement from that, in particular in the hardest puzzles, so in the challenge and the value set. And if we compare these to external chess engines, so Stockfish 15 and Crystal is a variation of Stockfish that is specialized to puzzles. So we got pretty similar numbers. Stockfish is probably stronger, but it still faces hard time with those puzzles. We did some studies on this Penrose position, so we wanted to understand why it's so hard to AlphaZero. So what you can see here is the position. So here, essentially, black is locked, and black has more material, but only this same color bishops are outside, and black cannot mate white. So what white needs to do is just to move with the king anywhere, and black cannot win, so it's a draw. And the thing is that if you look at the outputs of AlphaZero, so here on the prior and the value and the MCTS value, you can see that AlphaZero thinks that it's winning, and then if you let it planning, it thinks that it's losing. So these are like the black bars are up and down here. And what we did, we took those positions and we allowed AlphaZero to play from them. So we essentially started reinforcement learning from these positions. We didn't give it the solution, we just allowed it to play. And if we do it, we get those blue lines. So AlphaZero basically learns to understand the position. So it learns to predict the correct thing through self-play. So the point is that these positions are not fundamentally hard for AlphaZero, but it's probably that it hasn't seen them, and it's very unlikely that it will reach them. So to further study this question, we did this study where we allowed AlphaZero to train on all the positions. And then at the beginning, you see the numbers are pretty low. It can only solve a low number of the positions. But then if we let it to train on puzzles, the numbers start to increase. And then we did a few other things like improving the exploration, showing it intermediate positions, so advanced lines from the position. And we did some data augmentation to the half move clock. And we managed to solve all the positions just out other than one. And we still don't know if this position is actually correct or not. But it was interesting that, just by showing the puzzles, it still couldn't solve all of them. And it also suggested that, because it was so efficient to show it the positions, then probably it's a problem of exploration and out of distribution generalization. Yeah. So this is for the ELO. So here you can see matchups between AlphaZero and AlphaZero-DB, so different latents. We picked an opening book from the TCEC competitions selected by Matthew Sedler. And these positions introduce some advantage to one side, and we play them symmetrically. And you can see that all of our players are slightly stronger than AlphaZero, but in terms of ELO, they are roughly better the same ELO. So like this player 0 is slightly better than the others, 30 ELO compared to 25, but that's probably at the range of noise. So they are overly the same strength, slightly stronger than AlphaZero. Then we also looked at sub-additive planning and max over latency in this case. So what we did was in each opening, we split, we took some training seeds and we looked which agent was the best. And then we applied the sub-additive score on this. And we found that we basically could identify which player is stronger from each position. So they kind of spatialize and we can identify which one is stronger from which position. Not by a lot, but another 20 ELO improvement we got from that. Yeah, and this is just showing you, so if we pick some specific openings, we can see that, in some of the openings, all the players get roughly the same scores, but in some openings, we clearly can see that, one player is better than the others. Yeah. Okay, here, what was interesting, so we compared a smaller agent, so here only 5 players. We compared an agent trained with diversity with just 5 seeds of the same agent. So we wanted to see if, just by running multiple seeds, we can get to the same results. And these are the dashed lines. So you can see that with diversity, we got better numbers, but simply with seeds, you can also get some diversity bonuses. So there is some variability from randomness, but there is a clear advantage from having diversity as well. Let me skip this one, and also this one. Okay, so going to the summary. The idea, as I started, was to train this league of different players and to see if they can spatialize, if they can complement each other, if they can solve more things as a team. And I think we've seen that. They spatialized to these different openings and they could solve different puzzles. We observed these diversity bonuses, mainly in the challenge set, so in the more challenging puzzles, and also in the chess matchups. And this Penrose position was very important for us. And I think what we've seen is that it's not incomputable. So if you let AlphaZero play from it, it can solve it through some computational process. But it's still challenging if you don't do that. And some of our agents with diversity were actually able to solve it. Some open questions. So we've seen some overfitting of the diversity to the simulations we used in training. So because we do what we call behavioral diversity, the diversity that we optimize is actually affected by how many simulations we let AlphaZero to plan with during training. And what we've seen, and I didn't have enough time to go through, but I can quickly try to show it in this figure here, is that these are what you see here is the relative improvement from increasing the league size. So if we only include one player, it's 0, and then if we include more players, you get better bonuses. And what you can see here is that the biggest bonuses that we got from diversity was with this 5 to the power of 4 simulations, which is what we used in training. So it's not like we suffer from diversity at any budget, but the most that we got was using the same simulation budget. So that was interesting, and I think it's an open question of how to improve that. Another thing that I mentioned was that we couldn't do sub-additive planning with just root statistics. So root statistics is essentially without MCTS. And if we could do that, then we could start thinking about combining them inside the planning, which is what we call super-additive planning. So far, it didn't work for us. And with that, I'll leave short time for questions and say thank you for listening to us today.
All right, well, thank you very much for the excellent talk. That was fantastic. I think we probably have time for like 1 or 2 questions, and I'm going to assert my tyrannical privileges and ask the first one, which is qualitatively or quantitatively, how does this differ from just kind of expanding the like width of the search in MCTS, right? I'm curious for your intuitions around that.
So we tried it as a baseline at some point, and it didn't work the same way. And I think that the point is that I used to have a plot about that. But essentially, if you try to do wider search, you will end up sacrificing depth. And with quality diversity, you kind of have like you still have short beams, but going to different places. So you still go deep. You still go deep, but to different places with the different policies. So it's hard to find like a good balance to go very wide. Yeah.
Okay, thank you very much. And I guess one question from Seth, and then we'll wrap this up.
Cool.
Hi, thanks so much for the talk. My question, I guess, was about I didn't grasp my hand around. I guess in the puzzles it makes a lot of sense, but in terms of diversity, one of the things that you always have to worry about is what's the overall benefit? Is it actually improving it? And I was really convinced by the evidence in the puzzles, but I was wondering if you have any thoughts towards how this could actually improve the models at the task at which we're trying to solve, which I guess in this case is the game of chess.
So I guess my intuition is that so we know that these agents make mistakes, and the hope is that they make different mistakes. So the hope here is that, if we'll train them to be different, they will make different mistakes. And then if we'll have a large population, using these sub-additive or super-additive planning, we'll find a way to complement for them to complement each other. So that's the hope here.
Thanks.
Cool. I'm turning off the recording now.